All right, hello there. Today we're going to learn about normal distribution and z-scores. This is your statistics unit, day 2. So let's write that down. This is our statistics, day 2. You are going to learn about the normal distribution, and z-scores. Now, I put a file in a blank file of this in your in the Google site. If you want to print it out, it is a lot to print out, and so if you just want to maybe save the filled out file and refer back to that, or have it open while you're doing your math space, that should be enough for you there. So again, don't feel like you have to print out all these pages. It's quite a bit, and I just kind of pre-made them or grabbed some stuff off of math space, like some good examples that are going to be like your work that you have to do. All right, so what you have here. So you've maybe heard of the bell curve before. A bell curve, and so that's also, a bell curve is what you have when you talk about normal distribution. There's all different types of distributions, and a normal distribution, when you kind of graph out the numbers or like lay them out, they follow this idea. And what happens is that, in a normal distribution, most of your things are right in the middle, then a little bit less to the side and a little bit less, and it's basically symmetrical. It's like spaced out symmetrically. And so when you have a normal distribution, what happens to you is that your center is your average, your mean. But the center is also the median, and it's also the mode of your data set. So what's special about in a normal distribution is that the mean, median, and mode are all the same number. And 50% of your data points or your items lie below the mean, median, and mode, and 50% lie above it. All right, and you see these little marks here. Those are called standard deviation marks, and so we'll talk about those later, but don't worry about them for now. Now, when something's normally distributed like this, like I said, 50% above, 50% below, and a nice even symmetrical curve. So you might also get curves like this, or you might also see something like this. Let's say a lot of your data is at the beginning, and then it kind of drops off over here. This is not a normal distribution because everything's like pushed to the beginning. So this is not normal distribution. And then you might have a data set that has not a lot at the beginning and then a lot at the end. So this is not normal distribution either. These data sets are both skewed, one for the beginning, one for the end. A normal distribution has to look like this. It has to be nice, evenly spaced, a nice, simple bell curve. Okay? All right, so let's get to this first example here. Consider the following normal distribution. So an important thing, you have to be told that you have a normal distribution to use all these properties that we're talking about. And so let's look at this. It says, what is the mean? Well, the mean is sitting right here in the middle. What is the median? Well, because it's a normal distribution, the mean and the median are the same thing, and so is the mode. So easy question. All right, so I talked about those little marks on that graph there. So those little marks were standard deviation marks. A standard deviation is a measure of how spread out a group of numbers is, or a data set is. And so like if I look at this data set, you don't have to know how to calculate the standard deviation. And by the way, standard deviation, there is the symbols for it. In different situations, the symbol might be an S, or it might be a sigma. So that's like a little O with a little tail on it, I guess you could say. So an S or a sigma, those both mean standard deviation in different situations. All right, so this first data set, the standard deviation, you don't have to know how to calculate it, but you just have to know what it means, is 1.9. And the second data set, the standard deviation, is I calculated to be 10.9. So the reason that's true, or the reason those numbers are there, so notice the first data set. The lowest number is 5, and then we go to, 7, 8, 9, 10, 10, 11. So that data set is not that spread out. 5 to 11 are the lowest and the highest. But look at the second data set. Second data set, the lowest number is 4, then we go to 6, and it goes all the way through up and up and up and up till 35. So that is really spread out. If you're at 4 to 35, that's really spread out. So that's why you see the standard deviation here is a lot larger than, for instance, the standard deviation here, because the red data set is more spread out and the blue one is not. And so that's why the standard deviation is smaller. And so the standard deviation is basically what the words imply. It's a standard amount, so like an average amount that you deviate from the center. All right? And so that's what those little marks are. Now, in a normal distribution, those little marks occur at set percentages. And so that's what we're going to talk about next. So in a normal distribution, when you are one standard deviation from the center, that means that you have covered 68% of your data group. All right, so that means that basically we can break it up. This is 34% and 34% over here. So only if it's normally distributed, this happens. All right, when you're 2 standard deviations away, by the time you get to 2 standard deviations away, then you have covered 95% of your data. And when you're at 3 standard deviations, now you can go further, but there's not really that much there, you see. But by the time you're 3 standard deviations away, you can be assured that you have covered almost everyone, 99.7%. So if you break that down a little bit better, and this is called the empirical rule, this is what math space will refer to. But basically, your 68% divides up into 34% each. Then if you know the second group is 95%, well, 95 minus 68, I think I said 65, didn't I? Well, 95 minus 68 would be, let's see, 27%. If you divide 27% for this green area, you get 13.5 each. And so that's how you get that number. And then you do the same thing, 99.7 minus 95, and divide the remaining part equally. That's how you get this 2.35. So if you ever need to know how much this area is worth, it's worth 34% of your data. This area is worth 13.5% of your data points, and this is worth 2.35% of your data points. Okay, so in each of these are 1 standard deviation away from the middle. So this is 1 standard deviation above, because here's your center. Then this is 2 standard deviations above. This is 3 standard deviations above. So that's called your z-score, which we'll talk about later. Going this way, this is 1 standard deviation below. That's why it's negative. 2 standard deviations below. 3 standard deviations below. And usually you see graphs only go to 3 because after that, there's not really much left. All right, so I wanted to talk about the standard deviations just a little bit. So on a graph, you have your mean right in the middle. And depending, what your data tells you your mean is, that can also be thought of as 0. That's like you're at the center, okay, kind of like a number line. Then again, you are 1 standard deviation, so 1 standard deviation above, then you're 2 standard deviations above. So you're doing your mean plus 1 standard deviation, and your mean plus 2 standard deviations, and then your mean plus 3 standard deviations. Now, when you go backwards, you're taking away 1 standard deviation, you're taking away 2 standard deviations, and you're taking away 3 standard deviations from this number here. And so if you see a normal distribution set up, a lot of times they put 0, 1, 2, 3 to mean your standard deviations above and below, and -1, -2, -3. Now we're going to do some examples that have actual other numbers, and so you'll see what I mean. All right, so like this one. The results from the exam were approximately normally distributed. So again, somebody has to tell you that to be able to use all these rules. The mean score was 44, so you see that's marked right here, with a standard deviation of 6. So that means if I want to go up a line, I go up 6. So this should be 50. Then I go up 6 more. So you see 56, and then up 6 more, 62. All right. If I want to go back this way, that means I should go down 6. So 44 minus 38 is, minus 6 is 38. And take away 6 again, that should be 32. All right. So what's the x value on the graph? 32. What's the y value in the graph? 50. So just to see how that works a little bit. All right, so I have this picture here for us to save us some time. In the male population, the mean height was 179. So you notice the picture has 0, 1, 2, 3 and all. So this is going to be a different type of example. So I know that this is now 179. So if I want to go 1 standard deviation above, that means I have to add 11 to that. So I can cross this off. 179 plus 11, that would be 190. Plus 11 more, that would be 201. Plus 11 more, that would be 2 12. So I don't really need the 1, 2, 3 because I have like data values instead. If I want to go down, so 179 minus 11, that would be 168. Minus 11 more, that'd be 157. Minus 11 more would be 160, no, sorry about that. 146. All right, so in a male population, all right, so the question A says, how tall is Adam, who is 3 standard deviations above the mean? So Adam, 1, 2, 3, so 1, 2, 3 above, he must be 212 centimeters. Now you can be exactly a standard deviation, but you remember you can also fall in between, so those problems get a little bit harder. But how tall is Harry, who is 2 standard deviations below? So that would put him right here. So 157 centimeters. So today you're just going to do like very simple examples here. All right, so consider the normal distribution below. Each unit is on the horizontal axis, indicates 1 standard deviation. So if you want to, sometimes, you can draw these little lines here to help you kind of see everything. I put our little empirical rule over here. So we know here that this is 34% of our data. This one's 34% as well. And this last one right here is this matching this green one. This is 13.5% of your data. So by the time you know that, if you are at a standard deviation, if you haven't just gone halfway, you're at a standard deviation line. That gets a little bit harder if you're halfway, but you can just basically add up these percentages. So 34 plus 34 plus 13.5. All right, so it's 68 plus 13.5. That comes out to 81.5%. All right, so what percentage of scores lie in the shaded region? 81.5%. All right, so here, so I'm going to do this a little bit backwards. I don't really know what happens after 3. I mean, you do, but you don't really need to memorize those things. But what we can do is, the whole graph is 100%. So we can kind of think backwards. This half of the graph is 50%. And I know that this other little white part on the left is worth 34%. So 50 and 34, that's 84%. So basically what I want to do to get the little purple part is take 100% minus 84%. So it would be 16. So 16% is the purple shaded region. All right, this one here, same idea. So again, you can draw these lines on here to help you kind of see the groups right there. But when I look at this, let's use this rule right here. If I'm within 2 standard deviations on either side, that's 95%. And this one little piece over here is worth 2.35%. Okay, so the shaded region covers 95 plus 2.35, that would be 97.35%. And on math space, make sure you put the percent symbol because it wants it there. All right, so here, now this time it's not going to be generic here, it's going to give you some numbers. The times that a class of students spent talking or texting on their phones on a particular weekend is approximately normally distributed with a mean of 172. So I'm going to cross this off and put 172. The standard deviation is 6, so that means that this adds 6, I get 178. Add 6 more, I get 184. Add 6 more, I get 190. Take away 6, I get 166. Take away 6, I get 160. Take away 6, I get 154. So the question says approximately what percentage of students use their phones for between 160 and 184. So that means I want to go from 160 all the way to 184. So if I look at that region that I've shaded in, it goes from 2 below to 2 above. So that must mean I want this amount. So 95%. Okay, and it says use the empirical rule to find your answer, so that's what we're doing. All right, next one, similar question. The number of biscuits in a box is approximately normally distributed. So again, they're telling you it's normal distribution, so all these rules apply. The mean is 46 and the standard deviation is 4. So this one's 46, add 4, 50, add 4, 54, add 4, 58, take away 4, 42, take away 4, 38, take away 4, 34. All right, so complete the following sentence. Approximately 81.5% of the scores lie between 2 standard deviations below So that means I'm starting right here. And what? So I want to know, like, if I start at this red line and go to the right, when have I covered 81.5%? So let's see. So this first little group right here, this would be 13.5%. This next little guy right here would be 34 and 34. So I think I want those because I need to get all the way to 85. So 34 and 34 is 68 plus 13.5. Let's see, 5, 1, carry 1, 6, 7, 8. Oh, I think I found it, 81.5. So if I stop right here, I will get to 81.5%. So this is the region that gives me 81.5%. So it's a little bit backwards of the ones we were given before. All right, so it lies between 2 standard deviations below, and it looks like I stop at 50, so that's 1 standard deviation above the mean. All right, so from part A, this means that approximately 81.5% of the boxes have between 38 and 50 biscuits in them. Okay, all right. So next type of question, so a similar situation as before, but this one is going to be special because it's asking you, out of 400 divers, how many would be in the category? So let's figure out the rest of this first. All right, so the times that divers can hold their breath underwater is normally distributed, so it has to tell you that, with a mean of 141, so 141, and a standard deviation of 11. So let me add 11, so that gives me 152. Whoops. Add 11. So 163, add 11, so 174. Take away 11, so 130. Take away 11, so 119. Take away 11, so 108. All right, so it says 400 divers, how many would hold their breath for longer than 119 seconds? So basically what I want here is I want everything after 119. So again, when somebody includes like a whole side, I know that that can be counted as 50%. Because again, we don't know this little piece over here, and usually we're not going to need to. All right, so 50%, this one's 34%, and this little bar here is 13.5%. Okay, so 50 plus 34 is 84. 84 plus 13.5 would be 97.5. So 97.5 of the divers fall in this yellow area. Well, I need to know what's 97.5 of 400 divers, because the question is asking how many divers. So what I have to do is 400 times 0.975. Because remember, when you want to know a percent of something, you have to move the decimal 2 places to the left. So if you do 400 on your calculator times 0.975, you get 390. It came out to exactly 390 by chance. So my answer up here, 390 divers. All right. So next we're going to talk about, the last thing we're going to talk about is your z-score. So your z-score, when you see these little numbers down here appearing, what that was, this was 1 standard deviation above, this was 2 standard deviations above, this was 3 standard deviations above. So that is, actually you didn't know it, but that was your z-score. Your z-score is the number of standard deviations away from the mean, right, in a normal distribution. So if you are 1 above, you're +1, and 1 below, -1, all right? Now remember, I told you that you don't have to be a set amount. Like if you were, say, how about like right here, your z-score would be 1.5 because you are 1.5 standard deviations above. Let's say you were like right here. So your z-score for that spot might be like -1.2 because you're a little bit past 1. Let's say you were right here. Maybe your z-score for that is -2.3 because you're, a little bit past 2, but you're not halfway yet. So anyway, that's how it works. So z-score is the number of standard deviations away from the mean. And your z-score has a formula. So your z value is equal to x minus x bar over s. Or if you use in the other letters, it's x minus mu over the standard deviation. and that looks a little ugly, so I'll fix that up. The standard deviation looks like that. So I'm going to label these. In either case, these two right here are your standard deviation. This right here is your mean. So these two things, they're just different. These are just different symbols for different situations, whether you have a population or a sample. And so you don't need to know that yet. You just need to know that that's your mean and your standard deviation, whichever notation you want to use. Now the last thing right here is this X right here. That is your data value. It's like where you are. So if where you are compared to the mean divided by your standard deviations. Okay, so your z-score is going to be a number usually between -3 and +3. All right, so here we go. Frank finishes a run in 156 minutes. So that's his data value, his score. All right, the mean time taken to finish the race is 120, so that's your X bar. And the standard deviation is 12, so that's your S. So remember, your z-score is X minus X bar over S. So your data value is your X. So I'm just going to do 156 minus 120 over 12. So remember what we have going on right here. You have the center is 120. And then you got Frank over here, he's at like 156. And so I want to know how many standard deviations above he is. So this should come out to a positive z value because he is above the middle. Okay, so 156 minus 120 is 36. 36 over 12. So this came out to 3 perfectly. So that's his z-score is 3. It doesn't have to come out to a perfect answer, but it did. All right, so let's do last example. Kathleen scored an 83.4 on her biology exam, so 83.4 in biology, and the mean and the standard deviation were 81 and 2. So question A says, find the z-score for this. So let's go ahead and do that. So the z-score for the biology test, she got an 83.4 minus 81 over 2. So 83.4 minus 81, that's 2.4 divided by 2. So 2.4 divided by 2 is 1.2. So she was 1 standard deviation above the middle, 1 and a little bit more, so 1.2. It's a little bit past the first bar. All right, so next she took a geography test. So on her geography test, she got a 60 on her geography exam, and the mean score there was 46, so she actually was pretty far above it, and the standard deviation was 4. All right, so let's calculate the z-score there. So the z-score for the geography test was 60 minus 46 over 4. So 60 minus 46, let's see, that's 14, and 14 over 4. So 14 divided by 4 is 3.5. So compared to the rest of the class, she did great on her, even though her score was a 60, she did much better comparatively than she did in her biology exam, even though her biology exam, 83.4, pretty good. So if you had to answer which exam did she actually do better in compared to the rest of your class, you know, like when your teacher tries to curve your test and things like that, she did a lot better than the middle in her geography test. And that is it. I'll talk to you next time.